Hello, everybody. We're going to be talking about galvanic cells, how they work, and um, what type of voltage they make when you make them, and how to draw them, and all that wonderfulness today. So, as you see here, a galvanic cell is a device in which chemical energy, as we've been talking about with redox reactions, those electrons are captured rather than just being transferred. We're being capturing them into electrical energy. So essentially a battery. It can be the opposite of electrolysis. If you remember from ninth grade, you took energy, electrical energy, put it into the water, and when you did that, you separated the water, but you had to put energy into it to make chemical energy essentially. So you're putting electrical energy in. So it's kind of the reverse. We'll talk about electrolysis more on Thursday. We'll be talking about electrolysis, the opposite process. So, in a redox reaction, substance being oxidized and one's being reduced, as we've been talking about the last couple of days. The reactants collide with each other. The electrons are transferred. Heat is released, but there's no useful work being done. We just move the electrons from one substance to another. So, how can we capture those electrons and actually have something? How do we get that battery? So that's what we're talking about today. The answer to that, as far as how to make that happen, is to separate them. Separate the thing that's doing the oxidizing from the thing that's being reduced. And what it's going to require is the electrons will be transferred through a wire. It will not go just directly from one substance to another. So if those electrons can flow through a wire, they also could be going through a device, say a phone or a toy of some sort, or the computer that I'm using to record this with right now. It goes through there, it can do work or run some sort of electronic device. So there are two problems. If there is a problem, if two solutions are connected by a wire, the current will flow, but then it will stop. What happens is a charge will build up as we're transferring electrons from one substance to another. One side becomes built up, lots of electrons there. The other side has a slightly positive charge, and the flow will not continue unless we do something. So it would take a lot of energy to keep the electrons flowing, but we can fix that. The solution is what's called a salt bridge. Sometimes you'll see, show you two slides from now, as you can see on your sheet. There is a picture with a porous disc, but typically everything we're seeing from AP will have a salt bridge in it. So I'll show you what that looks like more so. So what does that salt bridge do? So there's a bridge between the two solutions, allows the ions to flow without actually mixing those solutions. It'll complete the circuit. The electrons flow through the wire. The ions flow from one solution to the other. So the ions are sitting in that bridge. And what happens is to keep the charges balanced, the ions from the salt bridge will flow towards the anode or the cathode. The cations will go to the cathode, the anions go to the anode. It's a very good song. But that's what ends up happening. I'll show what that looks like on the next slide. So it allows the electron ion flow, the net charge of 0, so we're not building up one or the other. So on your next slide, you have this picture, but you have some issues with what you can actually see in there probably. So this is a zinc sulfate solution. So what that means is there is zinc ions, 2+, and sulfate ions. The sulfate ions, that's supposed to be a 2. The sulfate ions really aren't that important for the process, but they are in there since it's a zinc sulfate solution. This electrode is zinc. So that is an electrode that, since it's a metal involved right now, the electrode is zinc. When there's no metals involved in the future, it'll be a platinum electrode. It's just an electrode that is inert that can help transfer the electrons. And I'll show you what that looks like in a little bit also. So this is a zinc electrode. This is a salt bridge. Inside of there, it shows that there's sulfate ions again. A lot of times they'll use nitrate as the example, sodium nitrate instead of sodium sulfate. But there's sulfate ions and there's nitrate ions. So what happens is these, and I'll talk about the anode and the cathode in a bit. I'll wait on that a little bit. In here we have copper sulfate, so there's copper ions. It's copper 2 sulfate. So copper 2 ions and then more sulfate again. So there's sulfate everywhere. The sulfate in these two solutions really aren't doing much. The sulfate here is moving, but we'll talk about why. So what happens here is the zinc is the anode. Why is it the anode? Well, if you look at your electron potential chart, you will see that the zinc is more likely to be oxidized. How would you know that? Well, let's look at both situations. We have both of these copper and the zinc ions. If we look at your chart, the copper is higher up on the chart. So the copper, Cu2+, plus 2 electrons making copper, is more likely to happen than the zinc ions making zinc. So what's going to happen is the thing that is most likely to be reduced will be reduced. Whatever is most likely to be oxidized will be oxidized. So the higher up on the list will be reduced. The other thing will get oxidized. So if I take the zinc formula that's on your green sheet and reverse it, the zinc going to zinc 2 plus 2 electrons, this is where the oxidation will occur. This is where the reduction will occur. Oxidation is called, or the place where the oxidation is called the anode. And I know that's on the next slide for you also, but I would like to label everything on this diagram for you. This is the reduction. The copper is where the reduction is happening, and that's called the cathode. And that is very tough to read. But this is where the cathode, and you can see it's right here too. But that's the cathode. And there's just a vowels and consonant line up there. Anode, oxidation. Cathode, reduction. That's my memory device for how that works. Some other things about this cell. Well, the anions travel to the anode. So here, these sulfate ions would travel to the anode. And the reason for it is because we are creating zinc ions, zinc plus ions. So those anions help balance out that total charge. Instead of having way too many positives, we add the negatives to it to try to balance out the total charge so it doesn't build up too much positive or negative charge. And here, the cations go to the cathode. So here's the sodium ions that are traveling towards the cathode. And you might say, well, why is that happening? Because we're reducing the amount of copper ions. The Cu2 plus, as you can see with this reduction equation, is turning into copper metal. It's actually going to increase the mass of this electrode here, because we're going to take some of these copper ions and turn it into copper metal. And by reducing the amount of positive ions, we need to replace them. So that's why the sodium or the cations are going to come there to try to balance out the overall charge and keep everything flowing. As we look at the anode here again, that's where the oxidation is occurring, where the electrons are being lost. So what's going to happen is the electrons will actually flow from the anode to the cathode. That's the electron flow. So that's the electrons are going from anode to cathode, and that is always the situation. So we have a lot of memory devices here. We have Leo goes Gur as far as the gaining electrons is reduction, and the losing electrons is oxidation. We have anode is where the oxidation occurs, and the cathode is where the reduction occurs. And then from A to C, I think of air conditioning, or I think of alphabetical order, that it goes from A to C, that's where the electrons are flowing. And then we have the wonderful song that the cations are going to the cathode, anions go to the anode. So a lot of things going on with this cell. But if you had this was given to you as far as what's the possibility, you'd have to look at the reduction potentials to make a decision of which things will be reduced and what thing will be oxidized. So that's what we're going to practice a little bit here also. So another way of looking at that same cell is here. It's the same cell, same electrons moving to the anode to the cathode. It's just showing things slightly different as far as the anions going through the porous disk instead of going through the salt bridge. But again, the salt bridge is the more typical way of showing it. So this has already been talked about, but these galvanic cells, this is a spontaneous reaction when it goes in this direction. and it is produced to do work. Oxidation occurs at the anode again, reduction at the cathode. So one thing that I do not talk about yet, and I'm going to show you the amount of voltage that could be produced with this one. So I need to go back to show you the copper, because we're going to do this with the next one, so I want to just show you ahead of time. It's a little bit jumping again, but here's the copper being reduced, and that voltage on your sheet, at least I'm looking in the book on page 901. I'm hoping your sheet is the same, but honestly right now I don't know, and I am just going to go ahead and do this anyway. Zinc becoming zinc ions plus 2 electrons. In the book, the reduction potential for that is negative 0.76, but now I've reversed it, so it's a positive 0.76. If I add those all together, I get what's actually happening here in this reaction, which should look familiar to the first day we talked about electrochem with the reaction that we did. And then the total voltage of the cell should be 1.10. And if you hooked up the two, and I might even show you this tomorrow if we didn't get to it at all today, but if you hook up the cell that's on the cart, we should get a voltage somewhere near 1.10. We do have some issues sometimes with some of the voltage being lost because of not perfectly clean wires. There's some oxidation on the outside of them or whatever, but this is how you can find out the voltage. Take the thing that's being reduced, keep the number the same, the thing that's being oxidized, and you reverse the number, and you get a positive voltage. That positive voltage indicates it is a spontaneous reaction, and that is the amount of voltage you will get when you mix them together. Moving on. So we're going to do some practice together here quick. So if we have the this cell, we're going to sketch it. We're going to show the flow, and we are going to take a look at how it all happens. So we got, first of all, think about what's being oxidized, what's being reduced in this situation. Here we're going from iron 2 to iron 3, so that means it's losing 1 electron. So that means that is where the oxidation is occurring with the iron. Here we have iodine going from a +5 to a 0. That is gaining 5 electrons. Each iodine gains 5 electrons. So that is the reduction part of it. So we have a lot to figure out here as far as how to draw this all out. First of all, I would want to balance the equation and balance the number of electrons that are all going on here. Calculating the cell potential, I'm going to wait on that for a little bit later slide. But I'm going to go ahead and start drawing this picture. I don't want this right here right now. So I think I can delete this. All right. So if we look at that given to us, I'm going to do a half reaction and just try to balance it real quick and show you what I mean by that. And then I'm going to end up erasing it to draw the actual cell. So the half reaction is involving the iodine because the iodine is going from a +5 to a 0, so it's gaining electrons. But you might notice that there's oxygens on one side, not on the other. So how do we account for that? Well, first of all, I want to balance the non-oxygens, so I'm going to put a 2 here because I have 2 iodines here. I want 2 iodines there. To balance the oxygens, I'm going to put as many waters as I need to give me as amount of oxygens there are. So I'm going to put 6 waters here. On the other side, I'm going to put as many hydrogens as I need to. And that is 12 to balance it on the other side. Essentially, this is something that's in an acidic solution, and we're going to have to take that into account when we do our drawing. If you look on page 901, you actually would see this reaction. It is kind of about a third of the way down. It is doubled in here because they put a half in front of the I2. I don't like to do that, but you can see that it has a voltage of 1.20. So this is the reaction that is, this is the reduction that's occurring. There's going to be how many electrons here? 5 electrons. That was if this be cut in half, so it's actually going to be 10 electrons in this situation. The other reaction is Fe going to Fe 3 plus, 2 plus to 3 plus. If I look on this sheet, going from 3 plus to 2 plus, it actually is reversed. If I look on page 901 again, it's almost halfway down because this is the oxidation. When I flip it like this, and on my sheet, on my chart, it says 0.77, so I'm going to reverse that to make it negative 0.77. So the higher one on the chart will be reduced. The opposite thing will be oxidized. And we already knew that because the equation gave it to us at the beginning. If we want to find out the voltage of it all, we'd want to balance the whole works and show that there's actually 10 electrons lost. So I'd multiply both these by 10 because we have to have total electrons transferred. And I could add those two equations together. I'm not going to do that right now, just for time's sake, because I'm almost out of time here. But if I add up these two voltages, that's actually something we're doing on a few slides down. We can find the cell potential of that. I don't think I'm going to be able to get through this whole packet, but I'm going to give you a good start here. So if I want to find out the cell potential, so I'm a few slides ahead. It looks like it's going to be 0.23 plus 0.2, so 0.43 would be my voltage. So essentially I did about 4 or 5 slides ahead where it says calculate the cell potential for the galvanic cell number 36. So I'm kind of doing some of the things ahead as it looks like how we're finding out the cell potential. And so I've kind of done some of those things already, but drawing this is where it gets a little bit more hairy. So I want to make sure you know how to draw something like this. Then you can do most of the homework problems that you want to practice. So let's go ahead and draw this out. So we're going to have, and I don't always have the anode or cathode one side or the other, but you'll notice in neither of these half reactions did we have a metal. We have iron ions 2 plus and iron ions 3 plus. And that is going to be where the oxidation occurs. So let's go ahead and put those in here. Let's do it over here because I want to do it, switch it up so you notice that's not always the anode on the left. So I need both of those ions. All the ions that are in the half reaction need to be in solution. If there was metal or iron metal, that would be my electrode, but there's not. There's only ions, so my electrode is going to be platinum. Just an inert metal, which is typically talked about as the ions, or as the electrode. So this would be a solution with those ions in it. So we have to have everything for each half reaction in the beaker. In the other beaker, we also would have a platinum electrode because all we have that is changing there are iodate ions, straight up iodine, but then we also had that there was H plus in there. It was an acidic environment, which is pretty normal that happens a lot. For instance, in your car batteries, we have sulfuric acid in there. It's an acidic environment that needs to be to make it work. So what would happen here is we would have a wire attaching those two electrodes. We would also have a salt bridge, which I did not leave space to draw worth anything, but I'll make something do here. So inside of here, I'd have ions, sodium, and very oftentimes nitrate is shown. I'm very low on space, so I'm going to put that there. Now the question is, what's the anode, what's the cathode? Well, we decided that this is where the reduction was occurring. So this is the cathode because that reaction had a higher reduction potential, so that is where the reduction would occur. And this is the anode because this is where the oxidation would occur. Now, other things that are often asked about, where are the electrons flowing? Well, the electrons are flowing through the wire from anode to cathode. So officially, the anode is that platinum wire right there, or platinum electrode. The cathode is this right here, so this side of the whole cell. What else could be asked? Where are the ions flowing? the nitrates flowing, because they're anions, they flow to the anode. The cations go to the cathode, so they go through the salt bridge down into there. Trying to think of other things I'm forgetting. It says show direction of electron flow, show the direction of ion migration, identify cathode and anode, give the overall balance. Oh shoot, I should have finished up that balance equation, but you could just add those two together. That's not too big of a deal. As you move forward, I mean, it's a big deal to be able to balance them, but that's something that you could do. So essentially the oxidation, we're pulling the electrons through, going from the thing that's losing them, the thing that's being oxidized, to the thing that's being reduced. You already have all that written down. Determining a half, we can write the half reactions, add up the two voltages from your green sheet or from your book. And I know that this is fast and maybe not done perfect because I'm trying to get this done since I'm going to be gone and I have other people gone for sports. Hydrogen is given a standard of 0. It doesn't need to be. It's really an arbitrary thing. I don't know why that was decided. Essentially, we could have had the very bottom one, which is lithium on page 901, and I believe it is on your green sheet too, be 0 and everything be positive. But when this was decided, to decide hydrogen was going to be the standard. Anything that reduces more than hydrogen is a positive value. Anything that reduces less likely to reduce in hydrogen is a negative value. And really all that matters is the difference between the thing being oxidized and being reduced anyway. But that's kind of a weird thing there if you didn't realize why we have positives and negatives. It's just kind of an arbitrary thing. It doesn't matter all that much. Combining a half reaction, we've already actually done this when I showed you how to get the voltages from before. So you have all that information already. We actually don't multiply it. People are like, well, if we multiply by 5, do we have to multiply the voltages by 5? And we don't. That does not change the voltage because we have more electrons, just to try to balance out the electrons in the two. So positive cell potential, that will run spontaneously. We'll see on Thursday when we're talking about a negative cell potential, we would need energy to make that happen, which is what happens with electrolysis. So calculating iodate and iron ions, yeah, I don't have this written. It's actually, nope, that's a different one. So at this point, with the examples given, let's just give you some pointers here before you start trying to draw cells yourself. If there is a half reaction with a metal in it, for instance, iron becoming iron ions, the iron metal would be the electrode. The iron ions would have to be in a solution with it. If there's two ions or there's gases or things that are not metals within the half reaction, then platinum is your electrode for that anode or cathode. Those are things to definitely think about. But using page 901 is going to be helpful because some of the electrode or some of the potentials that you're going to see in problems in the book may not be on your green sheet. So if you have questions, be sure you let me know.